Good morning. This is for Unit 7, Day 3, Polar Coordinates. And the goal of today is to be able to take our traditional rectangular coordinates that are in the form xy and rewrite them kind of as these polar coordinates in the form of our theta. So normally, if you were to, on your calculator, turn it on, so if we just kind of did that and hit our y equals button, we would have, y equals, and then, I could graph something like y equals x, and it would show us y equals x on there. Well, now what we're going to be doing is we're going to change the mode of our calculator, and we're going to go down to that fourth line and go over to where it says polar, P-O-L, okay, and we're going to select that. And you'll notice when you quit, now when you hit your y equals, there will be r's there. And that r is for the radius, and we'll be able to kind of graph some of these on there. So just for example, if I graph something like 2 cosine theta, you'll notice now when you hit that variable key, it'll be a theta in there. Then you can graph that, and you'll kind of see, that circle over to that right-hand side. And I could zoom in if I wanted to on there. So, I don't know, maybe just a regular zoom in would do fine. And you'd be able to see it a little bit better. Notice there it looks a little more like an ellipse. If you wanted to zoom square, that'll definitely make it look more like a circle. These questions on the AP exam will appear as both calculator and non-calculator, depending on the type of question. So I wanted to kind of show that calculator move on there. And then let's talk a little bit about these polar coordinates themselves here. So there's several different types that you may be asked to graph. And the first type is a circle. So circles can have the form r equals, some constant cosine theta. It's a circle where a is that diameter, okay? And when it's a cosine, the circle has the leftmost edge at the pole, or the origin in this case. So here would be an example of, maybe this is 2 cos theta, and this would be a diameter of 2. And notice that its leftmost pole is at the origin there. And then if I was to graph, on that same calculator there, if I was to graph something with a sine, so I don't know, 4 sine theta, okay, and I was able to graph that, you would see that that not only is bigger, now I want to, notice when you hit your window, now it's your theta min, your theta max, and your t-steps, but I'm just going to zoom out so that I can see kind of both of them. So notice there's that cosine one there, and the sine one is on top. That number in front, so that A is still the diameter, but this time when you change it from a cosine to a sine, now the bottom is there, so it's kind of on top of the x-axis if you're looking at it that way. And there's an example of each of those there. So those are circles. And then one of the other things you may be asked to graph is a limison. And so that is of the form where there is something added or subtracted here, and then you've got that cosine. And again, it could be of the sine, and that'll just kind of change the shape of what's going on. So you can have, if it's a sine, it'll kind of be mostly above the x-axis, the horizontal axis. And then you can also be below if that's going to be negative. So you can kind of play around on your calculator and see. And so sines, you're thinking, again, the above and below, just like up on this example, the sine was above, or it could have been below. And then with the cosines, you're going to be thinking more left-right. So it would be on, the left and right of the y-axis there. And something special about these is you're going to have to really pay attention to the ratio. So the ratio of that A to B. You can kind of play around with it and graph a few different ones. When A divided by B is 1, you get that kind of heart shape. And then you can have some where there's a loop in them. Okay, those are pretty popular. And sometimes these are called cardioids when they look at the heart. And then other times you can barely see it. It's just like a very small, it's almost like a dimple. Okay, looks like a little garbanzo bean, or sometimes it looks like a little baby butt or something there. So you can have those. Those are all of the variety of this limison. And you've got those, and again, what's important on those is the ratio of those two numbers will kind of determine that shape, whether you get the loop, whether you get the heart, okay, whether you just get a little dimple, or if it almost looks like a circle with just a little push in it. It's more like it flattens out versus the dimple. And one of the more popular ones is the rose curve. Okay, so rose curves of the form, you could be sine or cos again. But the difference here is there's no plus or minus sign between. You can kind of see the difference here. There's a plus or minus sign with the A and B. Here, there's no plus or minus, but there is a coefficient with that theta. And these are going to be interesting because that's going to help determine your number of petals. So when n, that number in front of the theta, is even, it'll have double that number of petals, and when it's odd, it will have exactly that number of petals. So you can kind of go in here. We'll clear these out this time. And so say you had something like 4 sine of 2 theta. Okay, so when I graph that, that's going to have 4 petals, and those are pretty, and you can actually get some really beautiful looking graphs on these. So there's one with a sine, and if I did that same thing, only I changed it to a cosine, okay, you'd see there that it still has 4 petals, okay, but the orientation is slightly different there. So we said that a cosine graph will have the petal cut in half by the x-axis, okay, whether it's even or odd. And your petal length is actually that coefficient there. And the lemniscates, those are kind of our figure eights or the infinities. I put them on there just so you'd kind of be familiar with them. These are not really on there quite as much. I would say that the main ones that they like to focus on are the roses and the lemniscents. Okay, so it's just kind of an intro into the polar, and then we'll take a look at the next page in just a second here. Okay, so if you were to kind of determine which each of these were, this one here, so you have r equals 4 cos theta. Now, again, you could type this into your calculator, but you should be able to kind of recognize what this is without it. So this is going to be a circle, and its diameter is going to be 4. Okay, so it's a circle with diameter of 4, so I kind of write circle with a diameter equals 4. And since it's a cosine, that means it's going to be lying to the right-hand side of the pole there. So 1, 2, 3, 4 was that diameter, and I know my circle is not beautiful and perfect, but we're kind of thinking that's what that one's going to look like there. Okay, so this has that A and B with that plus sign in there, so this is definitely going to be a lemniscent. Okay, so I'm going to write that down. Oh, that's an O there. All right, and so the one thing you want to look at is the ratio. So here, A divided by B, well, in that case, it's 1 over 3. If that's a fraction, I always kind of say if it's little, like if it's a fraction, it's going to be with a loop. Okay, so that's going to be a loop. And since it's a sign, it's going to be above. Okay, and we're just kind of looking for sketches here. We're not looking for anything crazy. So we can take a look at this one. So you'd kind of do something like this, and it'd look like that, okay? And you could get into, you know, the lengths of this little inner piece versus that by kind of looking at those numbers in there. Okay, and over here, this is going to be another circle. Okay, so this is a circle. This time the diameter is 3. Okay, and since it's a sign, that means it's going to be above. So I think it's going to look something like this. So a diameter of 1, 2, 3. So I'm going to have circle there, and then again, it's a sketch. So it's that looks a little bit elliptical, but there's the best circle I could freehand there. So notice that this diameter is 1, 2, 3, and hopefully it's, you know, about 3 across that way since it is a circle. All right, and then it looks like, this is a rose. Okay, so a lot of people get confused between the circles and the roses. Notice that the rose is the one that has a coefficient with the theta. So this is going to be a rose. Okay, and since it's sine, I'm thinking it's going to be have symmetry for the y-axis, and it's going to have 4 petals of length 1. So this is 4 petals of length 1. So And it's hard to get a length one when you have when the y-axis cuts it, because it's nice if this was a cosine, you'd have that length of the petal on the x-axis, but I don't have that here. So this length there is going to be 1, but it's kind of hard to do that on here. But I've got something like that. And then over here we have a lemison. And this time, my a divided by b, it's another fraction, so a over b is going to be 1/2, which means it's going to be a loop, but this time it's a sine curve, so it's going to be to the right. Amelia thought these were so easy, she wanted to help a little bit. Okay, so I'm going to have that loop on the right-hand side, and then I'm going to go, and these, they do kind of go a little bit below there. That was not a great drawing there. So they will go a little bit, on the other side of the axis there, because it kind of dips below, but it's kind of close there. Okay, and the last one here, this is going to be a rose, okay, and since it's a cosine, I know that the x-axis is going to cut one of the petals in half. I'm sorry, one of the petals will fall on the x-axis, I should say. And so it's going to be 3 petals. So this is a rose, 3 petals, okay, of length 2. Okay, so we've got this. So 3 petals, and then I've got a petal here, and then they're kind of symmetric, so it's going to go something like this. Okay, so we've got that. Kind of do that. Okay, so in pre-cal you may have just kind of graphed these only on the calculator, things like that, and then the other thing you did in pre-cal was try to convert between the polar and rectangular graphs. So that's where I'll kind of pick up the next video, and that one might be on the iPad. Okay, so have a great day for now.